Welcome to this detailed session on data fundamentals, the foundation of machine learning. Before we talk about algorithms, models, or artificial intelligence, we need to understand one crucial truth: machine learning is nothing without data. Data is the raw material that powers every intelligent system. Whether it is a recommendation engine on Netflix, a spam filter in your email, a fraud detection system in banking, or a self-driving car, everything begins with data. In this session, we will deeply understand what data really means in the context of machine learning. We will explore different types of data, how data is structured, how it is used to train models, and how it is evaluated. We will also understand important concepts like features, labels, training datasets, and testing datasets. Many beginners focus directly on learning algorithms. But in reality, strong data fundamentals are what separate average learners from real machine learning practitioners. If your data understanding is strong, model building becomes easier. If your data understanding is weak, even the most advanced algorithm will fail. So in this module, we will build that strong foundation step by step, clearly, practically, and professionally. Let's begin. In this module, we will cover 5 major areas that form the core of data fundamentals in machine learning. First, we will start with an introduction to data in machine learning. Here, we will understand what data actually is, why it is important, and how machines interpret data differently from humans. Second, we will move to data types and structures. We will explore structured versus unstructured data, numerical versus categorical data, and how different formats affect machine learning models. Third, we will discuss training data and testing data. This is one of the most important concepts in machine learning. We will understand why data must be divided, how models learn from training data, and how performance is evaluated using testing data. Fourth, we will examine features and labels in machine learning. You will clearly understand what inputs and outputs mean in a dataset, and how features directly influence model performance. Finally, we will look at dataset examples and practical applications. We will discuss real-world dataset formats like CSV files, Excel sheets, image datasets, and text data, and understand how they are used in real machine learning projects. By the end of this session, you will have a strong conceptual understanding of how data works in machine learning, and why it truly is the foundation of everything in AI. Now, let's begin with the first topic. Now that we understand what data is, let's talk about why data truly matters in machine learning. Machine learning is not about writing fixed rules like traditional programming. Instead, it is about allowing machines to learn patterns from historical data and make intelligent decisions based on those patterns. This slide highlights 4 major reasons why data plays a critical role in ML. Now let us clearly define what data actually means in the context of machine learning. At its core, data represents raw information collected from observations, measurements, transactions, and records. It can come from users, systems, sensors, devices, websites, or even manual entries. In machine learning, data is not just stored information, it is the essential fuel that powers algorithms. A key insight to understand here is this: without data, machine learning cannot function. Algorithms do not create intelligence on their own. They extract intelligence from data. That means the performance of any model depends heavily on the quality, quantity, and relevance of the data it receives. Let's look at some practical examples. Customer purchase history is data. Weather measurements collected over time are data. Medical records stored in hospitals are data. Even social media interactions, likes, shares, comments, are forms of data. All of these datasets can be analyzed to uncover patterns and insights. Now, one of the most important principles in machine learning is garbage in, garbage out. If the input data is incorrect, incomplete, or biased, the model's predictions will also be unreliable. Even the most advanced algorithm cannot fix fundamentally flawed data. This is why data quality directly determines model success. In summary, data is the raw material from which machines learn patterns, recognize trends, and generate predictions. It is not just important, it is foundational. Now that we understand what data is, let's move to a deeper question. Why does data matter so much in machine learning? Understanding why data matters is critical for anyone entering machine learning. First, machine learning models do not rely on programmed rules. Instead, they learn patterns from historical data. This is known as pattern learning. For example, instead of writing rules to detect spam emails, we provide thousands of labeled examples. The model studies patterns in those emails and learns to classify new ones automatically. Second, data quality has a direct impact on model performance. 3 key aspects determine this. Volume. How much data is available. Quality, how clean, accurate, and complete the data is. Relevance, whether the data actually relates to the problem we are solving. If the dataset is too small, the model may not learn properly. If the data contains errors, missing values, or bias, predictions will be inaccurate. This brings us to the risk of poor data. Biased or low-quality data can lead to flawed decisions. In industries like healthcare or finance, this can have serious consequences. Poor data can damage business objectives, reduce stakeholder trust, and create ethical concerns. Finally, data understanding is essential before building any machine learning system. You must understand what type of data you have, what patterns may exist, what limitations are present, and whether the data aligns with your business goal. In real-world machine learning projects, data understanding and preparation often take more time than model development itself. So remember this clearly: algorithms are important, but data is more important. With strong data understanding, you build strong models. Without it, even the best algorithm will fail. Now that we understand the importance of data, let's move forward and explore different types of data and how they are structured. Now that we understand what data is and why it plays such a critical role in machine learning, let us look at the complete journey of data, known as the data lifecycle. Machine learning is not just about selecting an algorithm and training a model. It is a systematic process that begins long before model training and continues even after deployment. The first phase in the data lifecycle is the collection phase. In this stage, we gather raw data from various sources such as databases, APIs, sensors, business systems, websites, or manual records. The key focus during collection is relevance and completeness. If we collect irrelevant or insufficient data, the model will struggle to learn meaningful patterns. Therefore, understanding the problem statement before collecting data is extremely important. Once data is collected, we move to the cleaning phase. Real-world data is rarely perfect. It often contains missing values, duplicate records, inconsistent formats, incorrect entries, and outliers. During cleaning, we handle missing values, remove duplicates, correct inconsistencies, standardize formats, and detect anomalies. This step ensures that the data is reliable and ready for analysis. Clean data improves model stability and performance. After cleaning, we enter the exploration phase, also known as exploratory data analysis or EDA. In this stage, we analyze patterns, distributions, trends, and relationships within the dataset. We use statistical summaries and visualizations to understand how variables interact. This helps us identify important features, detect bias, and understand whether the data aligns with the business objective. Exploration provides direction for the modeling process. Next comes the preparation phase. Here, we transform the cleaned data into a format suitable for machine learning algorithms. This may include encoding categorical variables into numerical form, normalizing or scaling numerical features, engineering new features, and splitting the dataset into training and testing sets. Preparation ensures that the data structure matches the requirements of the algorithm. Once preparation is complete, we move to the training phase. In this stage, the machine learning algorithm is fed the training data. The model begins learning patterns and relationships between features and the target variable. It adjusts its internal parameters to minimize prediction error. This is the phase where actual learning occurs. Finally, we reach the evaluation phase. After training, the model is tested on unseen data to evaluate its performance. We measure metrics such as accuracy, precision, recall, F1 score, or mean squared error depending on the problem type. If performance is not satisfactory, we refine the model and repeat parts of the lifecycle. It is important to understand that the data lifecycle is not strictly linear. It is iterative. Often, after evaluation, we go back to improve data cleaning, feature engineering, or even data collection. In summary, the data lifecycle ensures that machine learning models are built systematically, ethically, and effectively. Each phase contributes to the final model's reliability and success. Understanding this lifecycle is essential for building strong, real-world machine learning solutions. Now that we have covered the fundamentals of data and its lifecycle, let us move into the next important section, data types and structures. So far, we have discussed what data is and how it moves through the machine learning pipeline. But not all data is the same. Data can exist in multiple forms, and understanding these forms is crucial before applying any machine learning technique. In this section, we will explore different types of data, such as structured and unstructured data, how data is stored and organized, how data format influences preprocessing techniques, and how choosing the right structure improves model efficiency. Understanding data types helps us decide which algorithms to use, how to pre-process the data, how to engineer features effectively, and how to avoid common modeling mistakes. Before building intelligent systems, we must first understand the nature of the data we are working with. So now, let us begin exploring data types and structures in detail. Now let's understand the difference between structured and unstructured data, which is a fundamental concept in machine learning. First, structured data. Structured data is organized in a predefined format, usually in rows and columns. It is commonly stored in databases, Excel sheets, or CSV files. Each column represents a feature, and each row represents a record. Because the format is standardized, structured data is easy to store, query, and analyze. It works efficiently with traditional machine learning algorithms like regression and classification. This makes it less complex and cost-effective to process. Now, let's look at unstructured data. Unstructured data does not follow a fixed format. It includes images, videos, text documents, emails, and audio files. This type of data does not fit neatly into tables. Unstructured data is typically stored in file systems or non-relational databases. Before using it in machine learning, we must perform feature extraction, for example, extracting text tokens from documents or pixel patterns from images. Often, advanced techniques like deep learning are required to analyze unstructured data effectively. In summary, structured data is organized and easier to process. Unstructured data is complex and requires advanced pre-processing techniques. Understanding the type of data helps us choose the right tools, storage methods, and machine learning models. Now let's look at some common examples of structured data to understand how it appears in real-world scenarios. One of the most common formats is CSV files. CSV stands for comma-separated values. These files store tabular data in plain text format, where each value is separated by a comma. They are simple, lightweight, and widely used for data exchange and pre-processing in machine learning projects. Another popular example is Excel spreadsheets. Excel provides a user-friendly interface with rows and columns, built-in formulas, filters, and pivot tables. It is commonly used in businesses for storing and analyzing structured data. Next, we have relational database systems, such as SQL databases. In these systems, data is organized into tables with defined relationships. Structured query language, or SQL, is used to retrieve, manage, and manipulate the data efficiently. These databases are widely used in enterprise applications. Finally, an important category within structured data is temporal data, also known as time series data. This type of data is ordered by time, such as stock prices, sales data, or sensor readings. Time series data is especially important in forecasting and predictive analytics. In summary, structured data is organized, easy to store, and efficient to analyze. It forms the backbone of most traditional machine learning systems. Now let's explore some common examples of unstructured data. Unlike structured data, unstructured data does not follow a predefined format like rows and columns. It is more complex and diverse in nature. First, we have images. This includes photographs, medical scans, satellite images, and facial recognition data. To analyze images, we use computer vision techniques that extract patterns, shapes, and pixel information. Next is text data. This includes articles, emails, customer reviews, and social media posts. Since text is not organized in tabular form, we use natural language processing, or NLP, to analyze sentiment, topics, and meaning. Then we have video data. Video is a combination of images and audio, making it more complex. It requires advanced processing techniques to extract visual frames, motion patterns, and sound features. Finally, audio data includes voice recordings, music, and sound signals. Audio analysis involves signal processing techniques to identify speech patterns, tone, and frequency. In summary, unstructured data is rich and powerful but requires advanced pre-processing and specialized algorithms like deep learning for effective analysis. Understanding these examples helps us recognize the real-world importance of unstructured data in AI applications. Now we are moving into the third major section of this presentation, training data and testing data. So far, we have understood what data is, why it matters, and the different types of data. But collecting and preparing data is not enough. We must also understand how it is divided and used during model development. In machine learning, we do not train a model on the entire dataset and evaluate it on the same data. That would lead to misleading results. Instead, the dataset is divided into different parts, primarily training data and testing data. In this section, we will explore What training data is and how it helps the model learn patterns. What testing data is and why it is essential for evaluating performance. And how proper data splitting ensures reliable and unbiased model results. Understanding this concept is crucial to building models that generalize well to new, unseen data. Let's now begin with training data. Now let's clearly understand the difference between training data and testing data. Training data is the portion of the dataset used to teach the model. It helps the algorithm learn patterns, relationships, and trends. Typically, around 70 to 80% of the dataset is used for training to ensure sufficient learning. On the other hand, testing data is used to evaluate the model's performance. It consists of unseen data, usually 20 to 30% of the dataset, and helps measure how well the model generalizes to new information. The key distinction is simple: training shapes the model's behavior. Testing validates its performance. One critical mistake to avoid is using the same data for both training and testing. This leads to overfitting, where the model performs well on known data but fails in real-world scenarios. Proper separation ensures reliable and unbiased results. Now let's look at how datasets are prepared and split. The process begins by collecting the full dataset and randomly shuffling it. After that, we define a split ratio, commonly 80 to 20 or 70 to 30, to divide the data into training and testing sets. The training dataset helps the model learn feature patterns and optimize parameters through iterative training. The testing dataset evaluates performance using metrics such as accuracy, precision, and recall. This ensures the model is assessed objectively. For example, when building a spam email detector, we train the model using historical labeled emails and then test it on unseen emails to check its effectiveness. A proper split strategy ensures fair validation and prevents biased evaluation. After training and testing, the next step is validation and evaluation. One common technique is cross-validation, where training data is divided into multiple folds. The model is trained and validated across different subsets to ensure stability and reliability. Next, we use performance metrics such as accuracy, precision, recall, F1 score, and confusion matrix. These metrics help us evaluate model effectiveness from multiple perspectives. Another important concept is balancing model complexity. A model that is too simple may underfit, while a very complex model may overfit. The goal is to find the optimal balance for strong generalization. Finally, best practice requires maintaining complete separation between training and test data until final evaluation. This guarantees unbiased results and realistic performance measurement. In summary, proper validation ensures that the model is not just accurate, but also reliable and robust in real-world applications. Now we move to the fourth key concept in machine learning: features and labels. So far, we have discussed data types and how data is split into training and testing sets. But to truly understand how a model learns, we must understand what features and labels are. In this section, we will explore what features represent in a dataset, what labels signify, and how their relationship enables supervised learning. Understanding this concept is essential because features and labels form the core structure of any machine learning model. Let's clearly understand the difference between features and labels. First, features. Features are the input variables of a model. They are independent variables, often represented as X. These are the measurable properties or characteristics used by the model to make predictions. For example, in a house price prediction model, features might include size of the house, number of rooms, location, age of the property. These inputs help the model learn patterns. Now, labels. Labels are the output or target variable, often represented as Y. It is the value the model is trying to predict. In the house price example, the label would be the actual price of the house. So simply put, features are the inputs. Labels are the outputs. The relationship between features and labels is what allows supervised learning to work. The model studies the input features along with the correct answers, the labels, and learns how to map inputs to outputs. A simple analogy is fruit recognition. The features could be color, size, and shape. The label would be the name of the fruit, apple, banana, or orange. In summary, features provide the information, and labels provide the correct answers. Together, they enable the model to learn and make accurate predictions. Now let's discuss feature engineering and selection, which are important steps in preparing data for machine learning models. First, feature importance. Not all features contribute equally to predictions. Some features provide valuable information, while others may only add noise. Identifying and selecting the most useful features helps improve model performance. Next is feature engineering. This involves creating new features or transforming existing ones to better represent the underlying patterns in the data. Good feature engineering can significantly improve prediction accuracy. The third concept is feature scaling. Since features may have different ranges, scaling them to a similar range helps algorithms perform more efficiently and prevents certain features from dominating others. Finally, dimensionality reduction. This process removes redundant or less important features, simplifying the model, reducing computational cost, and improving overall efficiency. In summary, careful feature engineering and selection help build more accurate, efficient, and reliable machine learning models. Now let's look at some real-world examples of features and labels in machine learning. First, in housing market prediction, features may include square footage, number of bedrooms, and location. The label is the house price that the model tries to predict. Second, in a medical diagnosis system, features could include age, blood pressure, glucose level, and BMI. The label represents the patient's condition, such as whether they are healthy or have a specific disease. Third, in email spam detection, features include information like the sender, keywords in the email, and attachments. The label indicates whether the email is spam or not spam. These examples show how different industries use different types of features, but the concept remains the same. Features provide the input data, and labels represent the outcome the model predicts. This demonstrates how machine learning principles can be applied across multiple real-world domains. Now let's move to dataset examples and practical application. In machine learning, understanding datasets becomes easier when we look at real-world applications. A dataset typically contains multiple records, where each record includes features as inputs and a label as the expected output. For example, in a housing price prediction dataset, features may include house size, number of bedrooms, and location, while the label would be the price of the house. Similarly, in a medical dataset, patient information such as age, blood pressure, and glucose level act as features, and the label could indicate whether the patient has a disease or is healthy. Another example is email spam detection, where features include keywords, sender details, and attachments, while the label identifies whether the email is spam or not spam. These practical examples show how datasets help machine learning models learn patterns from historical data and apply that knowledge to make predictions on new data. In summary, datasets bridge the gap between theoretical concepts and real-world machine learning applications. Machine learning datasets come in different formats depending on the type of data being analyzed. One common format is CSV files, which store data as comma-separated values. They are simple text files that can easily be imported into analytical tools like Python or Excel. Another format is Excel spreadsheets, which allows structured data storage with formulas and multiple sheets for better organization. Datasets can also come as images, such as JPG or PNG files. In computer vision tasks, these images are converted into pixel values that models can analyze. Finally, there is text data, which includes formats like TXT or PDF. In natural language processing, this text is transformed into numerical representations so machine learning models can understand patterns in language. These different formats allow machine learning systems to work with a wide variety of real-world data. Let's look at some well-known datasets commonly used in machine learning. The iris dataset contains measurements of flower species and is widely used for classification tasks. The MNIST dataset includes about 70,000 handwritten digit images. It is often used to train models to recognize numbers from 0 to 9. Another popular example is the Titanic dataset, which contains passenger information such as age, gender, and ticket class. It is used to predict survival probability. Finally, customer behavior datasets analyze purchasing history and demographic information to predict customer preferences or potential churn. These datasets help researchers and students practice building and testing machine learning models. Working with real-world data usually follows a structured process. First is problem identification, where we define the objective and determine what we want the model to predict. Next is data collection, where datasets are gathered from reliable sources such as Kaggle, public repositories, or organizational databases. After that, we load the data into tools like Python using libraries such as Pandas or NumPy. The next step is data exploration, where we analyze data structure, types, and statistics to understand its characteristics. Then comes data cleaning, where we handle missing values, remove outliers, and fix inconsistencies. Next, we perform feature visualization, using charts and graphs to identify patterns and relationships. Finally, we perform a train test split to divide the dataset into training and testing sets before building the machine learning model. Following this process ensures that the data is properly prepared for accurate and reliable machine learning analysis. Thank you everyone for taking the time to watch this presentation. I hope this session helped you understand the fundamentals of data in machine learning, including dataset types, features and labels, and practical applications. If you found this presentation helpful, please like, share, and subscribe to support the channel and stay updated with more educational content on machine learning and data science. Thank you again for your time and attention.